Looks like we can get started. Um, and today we're really happy to welcome Jiarong Wu, who's a postdoc at Courant Institute at NYU. And so I'll pass it over to you and look forward to your presentation and the discussion afterwards.
Yeah, thanks, Mara. Hi, everyone. Thanks for coming to my talk. My name is Jiarong. I'm right now working as a postdoc with Lorzana at Courant. And today there's a slight change of plan. I was going to talk more about my PhD work, which is developing high fidelity numerical simulation for ocean surface waves. But then I decided to also talk about my postdoc project, which is currently undergoing. I think it's more directly related to this community. Is a data-driven study of ARC flux parametrization using in situ direct measurements. Okay, so back during my PhD, I worked on ocean surface waves, and even though I didn't directly touch on the ARC flux, it was always with this big picture in mind that waves sit at the interface of the ocean and the atmosphere, so it directly interact with the very bottom of the atmospheric boundary layer and the top of the oceanic boundary layer. So it modulates all these momentum, energy, and heat flux. So my PhD work, I did these two configurations for two aspects of wind wave dynamics. One is these fully coupled two-phase simulation with a turbulent atmospheric boundary layer and evolving and traveling waves. So looking at wave growth and the feedback to the atmospheric boundary layer. And this is related to, and also there's still work actively being done as follow-up to get kind of the momentum flux, so the drag coefficient from these kind of high fidelity simulations. And the second configuration is a single phase simulation with a free surface. So we use this more computationally cheap configuration to study braking statistics associated with an ensemble of broadband wave field. And also the dissipation and turbulence generation due to braking. So this is also related to momentum flux, but more in the sense that there is momentum entrainment by these wave braking into the upper ocean. And also gas flux, because this kind of braking distribution related to white caps. So there's work being done to develop a framework physics-based from bottom up to get a gas transfer rate from braking. And yeah, I won't talk too much details about the numerical methods, but these are just some animations showing how the simulations are set up. So for the fully coupled two-phase simulations, we have almost monochromatic wave train to start with. Oh, sorry. And for the wave braking statistics and dissipation, we start our simulation with initial wave spectrum that is already a realistic wind wave spectrum, and we solve these layered equations. And here are just more videos showcasing the capability of the solver we use. It's an open source solver called Basilisk, written in C. So it's more like a general PDE solver, and it has a two-phase component. Where it specializes in multi-phase and interfacial flow. So this also has industrial applications, but in the geophysical context, it's been used to study wave braking, bubble breakup, and turbulence. So again, in the context of developing a gas exchange rate model. And also there's another component, as I said, the layered model, which is more like layered ocean and atmosphere and general circulation model. So it's cheaper and it's been applied to larger scale geophysical flows like tsunami or Gulf Stream. These are very high resolution simulations. And there is not yet the coupling between, in the sense between atmosphere and the ocean, but there's work actively being done on that front. And there's the last slide on this high fidelity ocean wave simulation. It's an application that is potentially of interest to this community. Towards the end of the PhD, I got involved in this project. It's a collaboration between Luc and Bertrand at LOPS and Tom at WUI, and funded by the NASA Ocean Vector Wind Science team to potentially apply these high fidelity numerical simulation to guide the development of signal retrieval algorithm for remote sensing. So when we want to measure these wind and current, and because of the electromagnetic wavelengths of these scattorometers and Doppler scat, they resonate with actually the capillary range of ocean surface waves. So hopefully through these high fidelity numerical simulation, we can get, for example, statistics of these wind wave kinematics, so that we know under what condition, how the waves behave, and that will help develop these algorithms. And this is kind of some preliminary results showing that in the multi-layer framework, maybe this video is not playing, it's a screenshot. When I have set up a box of, this is on the top is a box of 40 meters, with the peak wavelength of 40 meters. And the bottom is, as you can see, the peak wavelength is 10 centimeters. So we're really zoomed in to these capillary waves, and we added the effects of surface tension. So there is a difference in directly, you can see qualitatively the surface shape, and also in the spectrum. So we are applying these tools to this remote sensing problem. So now I will change to my second topic of today, which is my postdoc work on air-sea flux parametrization. As I have mentioned, there are actively work being done to develop these sea state dependent parametrization of air-sea flux. The reasoning is that we know that waves modulate these fluxes. There have been these recent works proposing sea state dependent parametrization from Boyne, Salvage, etc. And many other works are still being done with both numerical simulation, lab scale experiment, and well-designed in situ measurements to push this front. But until that is ready, what we have right now, what everyone uses in the state of the art is the bulk formula. And bulk formula, they express momentum sensible and latent heat fluxes as the following. So it's some kind of coefficient times wind speed times the difference of the state variables between the air and the ocean. So velocity for momentum, temperature for the sensible heat, and this humidity for latent heat. And so they're based on boundary layer turbulence theories like Mononobkov similarity theory. But a lot of these coefficients are also empirically fitted to dedicated in situ observations. And I think we really need to think about, at this point, the accuracy of all these air-sea flux parametrization and bulk formula, because well, I don't really need to stress this point, but accurate representation of flux is really important in coupled weather and climate models. And also all these flux products, they use bulk formula to compute fluxes. They're so widely used that we really need to understand their limitation and uncertainty. So yeah, this plot is from Cronin et al. 2019 is showing kind of the targeted accuracy for fluxes to be able to capture these physical processes at different temporal and spatial scales. And on the bottom is another more or less recent work showing that, so these lines NCAR, core 3.6, and ECMWF are kind of different bulk formula developed by different institutions. So this coefficient for momentum transfer, as you can see, for example, differs between these different bulk formulas. And again, this global map is showing kind of the SST difference in the coupled simulation just by using different bulk formula. So panel A is the difference between ECMWF and NCAR. Panel B is between core and NCAR. So really, although I'm not as really an expert in this, I'd say there's still limited understanding of the uncertainty of bulk formula itself. We kind of have analysis of uncertainty of in the state variables, how that propagate through bulk formula, and we can get uncertainty through comparing different flux products. But in this work, we're aiming at understanding better the limitation of bulk formula themselves. So this brings me to our approach, which I got hired by M² Lines and LEAP, which are these two centers, teams which are doing machine learning for climate science. So we are trying this data-driven approach to see if we can rethink bulk formula. And this has already been done for other types of parameterizations for other processes, and also has been done for surface fluxes. For example, this 2022 paper tried a machine learning model, but for land and atmosphere fluxes. So because it's a data-driven model, the order one thing is what data we have. So until I really got into this project, I didn't know that data is quite limited, like high quality, direct in situ measurement of air-sea fluxes. So right now we have these ship measurement, and this is a PST multiple cruises data from Chris Farrow and his team. This dates back to the 1990s, so it's over 20 years, multiple cruises, and there are about 20,000 hourly averaged samples, but only half of that remain after I kind of cleaned out all the naughty numbers. We have a few more recent ones. I haven't got my hand onto all of them, but for example, this atomic campaign, which has about 4,000 samples. There are also, thanks to some team of Zippo and Luke Lennon, they shared with me their measurement from towels and platform like Flip. Unfortunately, these data are of a slightly different format, and also they're pretty small. So for now, I've been looking at ship data. And I forgot to mention that by direct measurement, I mean these eddy covariance measurement. So these campaigns measure fluxes by measuring the turbulent fluctuation of for momentum, it's the turbulent fluctuation of U prime and W prime, the covariance of those two. And for sensible and latent heat is W prime T prime and W prime Q prime. And our goal here really is to learn a flux model, and we want to learn both the mean and variance. I'll explain that in a minute. The variance part is both for uncertainty quantification and for potential stochastic parameterization. And also, we want to figure out how much useful information there is in these limited data. Okay, so for the model, so we kind of we assume that we consider the observed variable x, which in our case is the wind speed, the temperature of the air, temperature of the ocean, and humidity of the air. And the outputs are these fluxes, which is the momentum flux, sensible and latent heat. And we assume that these outputs y follow a conditional Gaussian distribution with mean. But it's conditional because we say that the mean mu is dependent on input x, and also the standard deviation sigma is dependent on x. And really the motivation for developing a probabilistic model instead of a point estimate is even when, because of maybe imperfect observation and not accounted for inputs, so this is kind of summarized in this unobserved variable zeta. So even when the physical laws governing the fluxes of y as a function of x and zeta is deterministic, the relation between y and our observed variable x might not be. So that's why we're thinking about doing the probabilistic model. So assuming that the output follow this univariate Gaussian distribution, we use two neural networks to estimate the mean and also the variance sigma. And these ANNs, as artificial neural networks, they have learnable parameters theta. And we learn these parameters thetas by minimizing the negative log likelihood loss function. So this is basically saying that if we assume that the distribution is this conditional Gaussian, then the likelihood of observing a sample is as follows. So we maximize the likelihood of observing all our samples, which is equal to minimizing the negative log likelihood. So this is kind of an animation illustrating how the network learns both the mean and the variance at the same time. So this is for a 1D synthetic momentum data. So I artificially generated a bunch of data drawing from a distribution of wind speed and using some really simple relation between momentum and wind speed. So just to illustrate, because the variance is easier to visualize in 1D, just to show epoch is each iteration of gradient descent, how the networks are learning both the mean and the variance. So then I kind of moved from synthetic data to the real data I have at hand. That's the PSD data set. So really we're training really small networks here because the data set is so small. It's really, like, compared to modern day machine learning, this data set is really tiny. We don't need to do anything super fancy. So I did a very small networks, 2 hidden layers of 16 nodes. And these, just to give you a sense, these networks take about a minute to train on my laptop. And the really difficult thing is because we have small data set with noisy measurement. We really want to prevent overfitting. And this is done by using this technique called cross-validation. So for each training, we kind of hold out one of the subset of the cruises, making sure that the training data doesn't contain that subcruise. And then during training, we use that data that's held out to kind of validate and prevent the network from overfitting. So yeah, this is the cross-validation kind of tricks. And really, also we're faced with a pretty hard task in the sense that in machine learning jargon, the word generalization usually refers to your model's ability to adapt to a new unseen data, but drawn from the same distribution as the one used in training. But in all these subcruises, we see that because they are done in kind of different physical locations and also really the size is not that big, we often see a distribution shift, both in the inputs, such as wind speed and temperature difference, and the outputs, so the fluxes themselves. So really, we are asking the neural nets to do a pretty hard job at adapting a different distribution. So it makes evaluating them a bit hard. Yeah, but this is, I think I need to point out that this is kind of a unique to our problem and to this small data set. So these color-coded cruise lines are like how much samples there are in each subcruise. So for example, maths has about 3,000 samples, and I labeled it subset 1, and EPIC is subset 2. And some subsets contain more than one cruise. For example, the waltz, high wind, GS, and gas exchange got lumped into the same subsets because they have kind of limited number of samples. Okay, now I'll show some results. So this is how the trained neural nets predict the momentum sensible and latent heat. At first glance, you'll say that the ANN prediction is pretty close to the bulk formula itself. So ANN is orange and bulk is green. And it is indeed that the case that for all three fluxes, the ANN has pretty similar behavior to bulk formula. Also, out of these three fluxes, the sensible heat seems to be the hardest to capture for both ANN and bulk. So they're both missing a lot of the variability, but it could also be that the sensible heat measurements themselves are pretty noisy. And this is a more of a quantitative evaluation of the mean prediction, so the deterministic part of the model. We use this coefficient of determination R squared between a predicted Y hat and a Y, which is the truth. So it's basically normalized mean 1 minus normalized mean square error. So for a perfect model, R squared would be 1. And the smaller R squared is the less predictive skills your model has. So we can see this is how both the ANN and the bulk formula, and in this case it's core 3.6, do on these 6 subsets that I shown in the previous slides. So I should explain that there is a little bit of spreading in the ANN performance because I have trained one on each of these held out subsets. So I have like 6 neural nets, and I'm taking the mean and the spreading of these neural nets. But actually, the spreading is relatively small. So again, you see that the ANN and the bulk, they kind of have similar predictive power over all data sets, with the ANN potentially have less fluctuation between subsets. And also, when the bulk does poorly, the ANN also. So really there is, I guess bulk is kind of, if you accept that you only have these inputs, bulk is kind of a pretty good fit of a model, even in a statistical sense. But I should point out that in some subsets, for example, if we look at the sensible heat flux QS in this middle panel, applied to the subset 2, which is the EPIC campaign, both the ANN and core almost have no predictive skills. The R-square is almost 0. This is really highlighting the kind of distribution shift problem in each of these campaigns. So your predictive power will vary depending on where you apply it to. And unfortunately, I also did this for the crosswind component of the momentum flux tau y, and there seemed to be no statistical significance in. Well, bulk itself doesn't predict a crosswind component. And my ANN also doesn't produce its statistically significant results there. Also, I want to mention that during my literature search, I found that this kind of work has actually been done a while ago in 2007, way before this machine learning for science got popular. And because there wasn't really, the neural network wasn't really that popular, they called their model a nonlinear statistical model for turbulent air sea flux, but it's actually just a neural net. And it was motivated by the idea that when you compute the flux using bulk formula like core, there is some iterative process you need to do, because your similarity profile depends on the stress, the wind stress, and then so you have to, it's an implicit equation you have to solve iteratively. So motivated even by the computational cost, they try to replace bulk with an ANN, and also they say ANN and bulk, they produce very similar results in the prediction. But this is for the mean, so the deterministic part. This work also only looked at the deterministic part. So you predict one value of fluxes using inputs. But the added piece in our current framework is the variance prediction. So I'm still trying to parse through these. So these are some very preliminary results showing how the variance prediction looks like. For example, for the momentum, if I plot the colored map of variance prediction with different wind speed, so U10, and temperature difference, you see also for the first plot, it's the absolute value of the standard deviation. And the second plot is the fractional value of standard deviation, meaning that it's standard deviation divided by the value of momentum flux itself. So for momentum, the absolute standard deviation is largest. If you look at the absolute value, it's largest at high wind speed, and this is kind of to be expected. But if you look at the fractional standard deviation, it's largest at low wind speed. And this is, I think this is something that we know, that really the flux is poorly constrained at this low wind speed end. And for the sensible heat flux, at least in my current neural network prediction, I see a high standard deviation at both the low and high wind speed ends. And if I looked at the fractional standard deviation, it's also pretty high when the temperature difference is really small. This is again the problem that you're dividing. So your denominator, which is the flux itself, is diminishing at these small temperature difference range. But the other thing is I'm seeing almost up to 300% standard deviation for momentum in some areas, and also 100 to, so this 10 is 1,000% for sensible heat flux. And I don't know if I should trust these values I'm getting, and I'm still trying to understand how I can interpret these values. So this is ongoing work to interpret this learned uncertainty. So this is kind of the so-called aleatoric uncertainty in, again, data science jargon, meaning that this uncertainty in the data, and it can come from a few different sources. It can come from the measurement itself, also the sampling window, and it also can come from the insufficient input features. And that's what we usually call hidden physics. So you are not giving the neural net enough inputs to capture all the variance. Also, some of this is due to the fact that we have very few samples in these low wind and high wind regions. And also, as I have briefly mentioned in the introduction, compared to other uncertainty estimate approach, I was trying to find values in literature about these uncertainty, but I found that most of the work they discuss kind of intercomparison between flux products. So you maybe have different flux products and you compute the standard deviation between those, which is a different approach because there are many things that go to these flux products. You have your model, you have your data assimilation, and you have bulk formula. So it's all kind of lumped together. And there are also error propagation of state variables through bulk formula, assuming bulk formula is ground truth. This is again not what we are targeting here. Because this work really tries to evaluate the uncertainty of bulk formula itself. So this is, I hope to open discussion on this kind of uncertainty in bulk formula. Also, we are currently looking for a model to test this kind of stochastic parameterization. So ideally, a more or less simplified or idealized coupled model where we can implement, meaning that we have a probabilistic model, we have the mean, we have the variance, and at online testing, we will draw random samples from this normal distribution at each grid cell, and we want to see if it makes any difference to processes people care about if we see sensitivity to stochastic parameterization of ARC flux. The other thing is I've shown this with both the mean and the variance part captured by a neural network. In fact, we could also use existing bulk formula as the deterministic part. So we will basically be learning the variance in the residual. So this is a good way to kind of get a stochastic model if you don't want to change your deterministic part, which is one of these bulk formula. The last thing I will say is I've also made some attempts to perhaps link this data-driven approach to C-state dependent parameterization. So I have this data set, which is a ephemeral 30-year wave hindcast forced by ERA5 reanalysis wind. So what I did is I took these 3D data, so it's kind of wave information as function of time, longitude, and latitude, and I interpolated the ship trajectories, so longitude and latitude as function of time, onto these 3D hindcast data. And then I augmented my inputs. So now instead of just wind, temperature of air and ocean, and humidity, I add some wave information interpolated from hindcast. And I do this again to see if I capture extra variability in the flux. And unfortunately, so far, I don't see a positive gain from doing this. But I've also just started doing it. So there can be many things that I can try, like how I organize my wave information. And also, I think one possible difficulty is these kind of hindcast data set, they're pretty coarse resolution. They're a half a degree and also 3 hourly outputs. So this may be too coarse to get meaningful results. Maybe we need really co-located measurements of wave and wind, wave and other state variables like wind and temperature. Yeah, haven't seen yet, but I'll try a few other things. So this is not a definitive no. So in summary, I talked about my PhD work, which is developing high fidelity numerical simulation for wind waves in both two-phase and layered configuration for study of their interaction with the boundary layers, also for potential applications to remote sensing retrieval algorithms. And right now I'm working on a probabilistic model for air sea flux learned from in situ direct observations. And so far, we've seen that the deterministic part has very similar performance compared to bulk formula across different test sub-data sets. So really, it can be used as an alternative in some scenario. For example, if you have a Python code that you want to plug in just a flux model quickly. And the additional variance part provide us with an uncertainty quantification that I'm still trying to interpret, and also a way to construct a stochastic model. Again, we're looking actively for test beds, so if there's any suggestions, I'd greatly appreciate. And this brings me to my last point, and I'll stop, is I think we need to start thinking about uncertainty of bulk formula itself. And for this, we really need, because for now, our best bet is the in situ measurements. We don't have kind of numerical simulation that's available to provide us with flux at scale. So we need more high quality measurement data, sampling those high wind and low wind areas, and preferably measurements that come with their own uncertainty estimate, so that we can kind of better separate the measurement uncertainty and the model uncertainty. And moving forward, we need this is something I learned from like the machine learning data science community, is we need objective metrics to evaluate any alternative flux models. And this includes both offline statistical metrics like the R-squared I showed, and also a common online testing bed where everyone can kind of try their own flux model on, like something that's self-contained and kind of idealized, so that we might see the effects of flux on processes that we care about. And with that, I'll stop and I'll answer questions, and also acknowledge to Anish, Bia, and David, John, and NCAR for discussions, and the various observational teams for sharing their data, and the M² Lines and lead scientists for the machine learning part. And thank you very much.
Thank you. Thanks for that wonderful talk. So now we'll open it up to questions. Are there any questions here? So you can raise your hand, or if you can't speak, put something in the chat. And I guess I'll start out because I was really curious to hear more about what you've been saying about the uncertainty of the bulk formula. How do you see that being implemented? I guess, are you suggesting alternatives in terms of you talked a little bit about evaluating alternative formula, or are you suggesting that in any implementation of the bulk formula, there should be an uncertainty associated with it?
Yeah, so I think that is a way to kind of get an uncertainty associated with using bulk formula for any flux products you provide, but also when we run an online coupled model, say coupled atmosphere and ocean model, we could start thinking about so right now, for example, every hour the atmosphere and ocean exchange information, and this is done by bulk formula. So you apply bulk formula to every grid point. So we can think of adding stochasticity to that coupling process. So when you apply bulk formula, you're not just computing a deterministic value, you're kind of drawing from a normal distribution. The drawing from a normal distribution part itself is not that expensive. But just we need, well, these probabilistic model have provided us with the variance in, so we can use that to construct the normal distribution to draw from, but first we need to make sure that these values make sense. And also then we can think about the kind of noise we add. So we can add kind of spatially independent noise, but we can also add correlated noise. And then we need to kind of argue why we need spatially or temporally correlated noise. And basically these all need to be tested out in an online setting. So that's why we're looking for models to test this. I hope it makes sense.
Yeah, thank you. Yeah, and pass to Shikhar.
Hi, Jiarong. Very nice talk. I had a question about you said that when you use different types of data sets from different locations, there was the distribution of the data itself was not the same.
Yeah.
So, yeah, so so can you please tell me, like, if this difference in the distributions comes from the physics, or if the difference in distribution comes from like the measurements, the type of instruments they're using, or something else?
I think it's mostly from the geophysical location of these campaigns. Like if you're in the tropics or if you're in a higher latitude. If you're in a low wind region area or a higher wind area. So it is basically which range you're sampling. So the hope is like physics-based formula, like bulk formula, will apply no matter what the underlying distribution is. But in reality, when we evaluate them, it seems like the predictive score is dependent on the distribution.
I see. Yeah, adding to that, so when we just look at the distribution, the skewness, the spread, do the spectrum of the wind speed also vary? Like the slope of the spectra for all of these different regions also have different slopes, or like
Wind spectrum, you mean kind of
power density spectra, like -3, -2 spectra is there, right?
yeah, so these are So I'm right now taking all these measurements as like local measurement of a particular point.
Mm-hmm.
So everything is local. I don't have of
No,
spatial.
that we can plot the spectra in frequency
Yeah,
domain.
yeah. The thing is, these ships also move around,
I
so
see.
we're
Okay.
sampling both in space and time. So, yeah, I haven't. I'm treating them as individual, independent samples. You could, yeah, there are. We're trying something to kind of extract information about spatial and temporal correlation, but so far I haven't done it.
Okay. Yeah. Thank you very much.
Yeah.
Roger?
Yeah, thanks for the nice talk, Jiarong. I had just a couple of very simple questions. The first one is with the neural network,
Mhm.
what is actually the functional form? Do you have a table at different wind speeds, for instance, discrete points, and then you interpolate between that? So if you want to use that to predict the flux, I know how the bulk formula works,
Yeah.
but I don't know how this works.
Yeah, so I'll explain in words, but hopefully it makes sense. So all these nodes, um, they have a weight and a bias. So it's you time the input with a weight plus a bias, but then you add a nonlinear activation function to each node. So every node is you pass at each time you pass through a node, you get basically a chain of nonlinear function. That's why this older paper called themselves a nonlinear statistical model. So it's basically there's this universal approximation theory of neural nets saying that with enough nodes and layers, you can approximate any functional shape you want. So yeah, it's a bunch of weights and biases and nonlinear functions, and the the prediction themselves will be smooth in your in the input variables. So this is different from other approaches like random forest, where you kind of it's like a binary thing. So you get a zigzagged prediction. This is going to be smooth in your input. I hope it makes sense.
Oh, yeah, that's helpful. Uh,
Yeah.
so my other quick question is for the wind speed, UA up there, you mentioned just the wind speed. Do you use the relative wind when you do this fitting? In other words, do you account for the ocean surface current?
Yeah, that's a good question. But this data set I use right now, PSD, I don't see measurements of current, so I'm just using wind. That's why I say that's also there are different formatting of data between these data sets. Like some of them report a current speed, some of them don't. And some of them report wind speed at measured at multiple heights. So far, I haven't found a good way to use that information consistently across data sets, unfortunately. But yeah, that's a good point. Strictly speaking, I should use a difference between wind and current speed.
Yeah, okay. In the core 3.5 2013 article, they do claim that they improved or reduced the scatter by incorporating the ocean surface current measurements that they had. But I think it's probably true, as you say, that they weren't available for every measurement that they used.
Yeah, I was also hoping to get those campaigns that go into core, the most recent core. There, I feel like the climate campaign, etc. But we haven't got that data yet.
Okay,
Hopefully we'll
thank
have.
you.
Yeah.
Thank you. We'll go to Eric and then Sarah.
Oh, you're
Eric,
muted.
you have to unmute.
There we go. Hi. Good. That was fun. Although just to the organizers, I didn't get in for half an hour because someone forgot about me. Anyway, there's certainly lots more data. You know that. And people people other than me would know what the quality is, but there's lots more data than this. Other question is, you were asking that people who take measurements do more statistical characterization. Is there something about the way you take the measurement, or is it something about how you process it afterwards? Is there something that should be that should be measured, or something that should be done on a computer afterwards?
Well, I'm also definitely not an expert in this, but as far as I know, there's both the instruments part, like each instrument, when they report a signal, there is some uncertainty. So that is kind of standard. Like when you measure it, you should keep a record of it. But also, I have seen technical documents from Chris Farrow where they document how there is uncertainty associated with your averaging time window. So depending on if you average for 10 minutes, 13 minutes, and 1 hour, there's sampling uncertainty that get reduced if you average for longer. So that's kind of related to your processing. Yeah, but there's also a trade-off of if you average for too long, then you lose kind of a slow variability. Yeah.
Thank you.
Go ahead, Claire.
So really nice talk. You've sort of made a plea for more measurements. How many more do you think you need? And what would the requirements be if you were expanding the data set? Would you be wanting measurements in extreme environments and high latitudes, or just anywhere?
Yeah, I think from this kind of distribution standpoint, we want to sample more these like higher wind area where it's now poorly sampled. Yeah, I don't have a estimate of how much we need, but it's probably helpful if we kind of adhere to the same kind of format and way of estimating uncertainty across different measurements. Yeah, also as someone's commented, I don't have yet all the data that is there. So there's also we can make this more openly accessible for people. Like right now, the way to get these data is to ask people for it. So if there is more, we should like make good use of them.
I guess I can ask a follow-up, which is, what have you learned from, or have you learned anything from this work about what observations would be needed for prediction of fluxes?
So far I have adhered to the same kind of state variables that go into bulk, but if we have more kind of consistent measurement of, say, the wave condition, then we can start to systematically put them in and see if they capture extra variability. Because and also I think this is not really related to my current framework, but measurements at different heights would help, I think. Right now, we only have kind of a fixed height measurement of fluxes, assuming that flux is constant. But we know that might not necessarily be true. It's not something I learned from doing this uncertainty exercise. This exercise is more a way to objectively evaluate a model and to work with our current limited data to objectively say how much we can say about the data we have. And because the stochastic parameterization part is something that people who do other kind of parameterization are thinking about, like, for example, mesoscale eddies, momentum flux of subgrid scale. For mesoscale eddies, they're trying stochastic parameterization and seeing some improvements in some area. So I think it's something we can try at least to at least play with it and see if there is a difference before we go out there and get more data. It is something we can do with what we currently have.
Thank you. Are there any other questions? If not, then we can thank Jiarong once again. And next week we will have a talk by Ernesto Rodriguez.
Thank you. Thanks for the invite.
Yeah, thank you very much. And thanks for the really nice talk.
Thanks a lot. Great talk.